Hello everyone, my name is Anne and this is Breno, and today we'll be presenting our emergency department simulation model.
Hi, I'm Brano. This is our model. First, we start with the arrival station, where we have an arrival every 9 minutes, and then each arrival is divided into the 5 different levels that we have, and each level gets their own attributes. Level 1 and 2, they skip triage and they go straight to the bed bay. In levels 3, 4, and 5, they go first to triage, they all met in the bed bay. Then they go to the treatment station, they see the nurse, they see the physician. Then if they do need a diagnostic or not, they go to the diagnostic station where they do the lab, the CT, or the x-ray if they need it. Then they go to the processing station if they are admitted or not. Then if they are admitted, they go see the admission clerk in the ed or this station. If they are not admitted, they leave the system. And after those who are admitted see the admission clerk, they also leave the system.
Now, I'll walk you through the full animation of our ER model. This running animation shows exactly how patients move through the system, where queues form, and how each resource is being used in real time. We begin at the arrival station, where all patients enter the system. From here, there are 3 possible routes. 1. They go through triage. 2. They go directly to the bed bay. Or 3. They exit the ER immediately. Here we apply an important rule. Level 1 and Level 2 patients skip triage and go straight into the bed bay. But if they arrive and bed bay is full, meaning a queue is formed, these critical patients immediately leave the system, because in our model they are not allowed to wait for a bed. Levels 3, 4, and 5 patients go through triage, where we have 3 triage nurses. In the animation, you'll see patients queue here, where all triage nurses are busy. After being triaged, they also attempt to enter the bed bay. And just like level 1 and 2, if bed bay is full, meaning if they are waiting either 90, 120, or 180 minutes, depending on their level, they will also exit the system. Once patients reach bed bay, they are assigned one of our 12 beds. We modeled this by creating a 12-unit bed resource and linking each unit to a point in the animation, which allows us to visually place each patient into a specific bed. You can see the beds fill up one by one. Right next to the bed bay area, you'll notice a busy counter that shows in real time how many beds are occupied. These counters appear throughout the model. For example, we also show them the number of triage nurses currently busy, and later the numbers of physicians, nurses treating patients, and other lab techs. These counters help us instantly verify resources utilization as the model runs. After bed bay, patients move to the treatment station, where they receive 2 evaluations: their first RN nurse visit and their first physician visit. The treatment area uses 6 RN nurses and 4 physicians. The animation shows queues forming if all nurses or physicians are busy, and again, the busy counters update live so we can see exactly how many of each resource is being used. Next, the patient moves to the diagnostic station. This part of the animation includes lab, CT scan, and X-ray areas. The patient goes through the decision that determine whether they need each test. Each diagnostic area has 1 technician. And in the animation, we can see these technicians are busy, like the other ones. The busy counters beside each diagnostic machine make this even more obvious. After diagnostics, patients return to the processing station, where they receive their second RN nurse visit. Here, the system decides whether the patient will be admitted or discharged. Patients who are discharged move to the discharge station and exit the system. Patients who needs admission go to the admit station, where they interact with the admit clerk, and then they leave the system as admitted patients.
For our performance metrics, we first and foremost are keeping track of the length of stay per level. Notably, level 1s have an average length of stay of around 250 minutes, and this is due to their processing times being longer at specific stations, as well as them being more likely to need various diagnostics. We also are keeping track of how many entities we have in the system at a time, aka our total work in progress, as well as the left without being seen and that percentage, which stays around 3 to 4%, which we, through our research, determined to be acceptable. We also keep track of our throughput per hour, which is around 3 to 4 entities, which also is acceptable. We are also tracking the number of beds busy, as well as the triage nurses busy, physicians, and RN nurses busy. And notably here we see that the physicians' average busy time is around 3.5 to 4, and this we also determined to be our bottleneck of where we need to make improvements. And I just want to point out that the average physician being busy being around 3.5 and not maxed at 4, which would be causing that queue, is because every time a bed becomes available, they have to go through the RN process, which does add some time the physician wouldn't be busy. Also looking at our graphs, we have wait time and queue for our triage, bed, and physicians, which we also used in order to determine where exactly our bottlenecks were. And that's where we saw that the physician queue was the main bottleneck, but also that occasionally we do have a bottleneck at the bed queue. So we're looking mostly into increasing the number of physicians as well as the number of beds.
So for our improvement scenarios, we first started by identifying the major bottlenecks that mainly affect our system, so it helps us understand our system more. So we concluded that from our baseline model that our utilization for the physicians was around 87%, average waiting time was around 26 minutes, and the X-ray technicians utilization was around 84%, average waiting time was around 69 minutes, lab technicians utilization was around 72%. Average waiting time was around 21 minutes, and for our CT techs, the key waiting time was around 11.2 minutes, and the CT scan duration was up to 90 minutes. Baseline model, we had 4 physicians, 12 vets, 3 triage nurses, 6 registered nurses, 2 lab technicians, 1 X-ray technician, and 1 admin clerk. And as you can see here for our results regarding the waiting time, which we're going to be comparing that through different scenarios, we had the most at level 5, which was around 103 minutes, and the lowest was level 1, which was around 17.9 minutes. For scenario A, we added more physicians. We started with 5 physicians and keeping the other resources the same. So as you can see here, we noticed an almost cut off by half for level 5 and level 4 for the waiting time. However, for level 1 and level 2 was the waiting time increased. And also when we tried to add our physician to be 6 physicians, as you can see here, the results was nearly the same. Maybe we had 14 beds instead of 12 beds. As you can see here in the results, it was nearly the same without any improvements. And also we tried 16 beds instead of 12 beds, and as you can see here as well, we had no improvements. For scenario C, we added a split level decision after triage that sends level 4 and level 5 directly into a separate fast track flow without seizing a bed. So these kept the bed bay entirely and went straight into treatment and diagnosis. And as you can see here, for our results, all the waiting times increased, and mostly for level 5, which was 5 times the original waiting time. But for scenario D, we had to edit our baseline model, so we had the lab testing was moved inside the room, so it was done at the bedside right after the physicians, so patients no longer have to wait at the lab queue, which kind of removed our biggest bottleneck. And as you can see here for our results, we had a huge decrease in our waiting time, especially for level 5, which went from under 3 minutes to 55 minutes. We added one more triage nurse. And as you can see here in the results, we had some increase in our waiting time, and we had no improvements. Which was combining our scenario A, B, and E, which is adding 1 physician, 2 beds, 1 triage nurse, which kind of helped a little bit for level 3 and level 5, but however for level 1 and level 2 increased their waiting times. Based on results, we can conclude that scenario D was the strongest improvement because it removed the main bottlenecks, lab delays, and reduced the waiting times for every patient level.